Assalamu alaikum.
Walaikum salam warahmatullah. How are you, doctor?
Alhamdulillah, fine. How are you, doctor?
Fine, fine.
Doctor, your voice is a bit echoing.
So is it okay, doctor?
No, still echo. Doctor, can you check your mic?
Is it okay, doctor?
I guess so. A bit better. Doctor, I guess we need to wait for a few minutes for the audience to come.
Sure, okay, doctor.
जी अस्सलाम वालेकुम।
वालेकुम अस्सलाम।
वालेकुम अस्सलाम।
अस्सलाम वालेकुम मैडम।
Waalaikumsalam warahmatullah.
How are you, man?
Fine, fine. How are you?
Fine, alhamdulillah. Yes,
How
Atar,
is
shall we
it?
start?
I'm okay if everyone ready.
Okay, thank you. Bismillahirrahmanirrahim. Thank you, Doctor, for sparing some time to give some valuable thoughts to our students and faculty. I warmly welcome to you and the other participants who are joining and hopefully will join more to us. In the meanwhile, I welcome all of you to this event, this webinar, online webinar, and I'm very hopeful we will learn something from you. Today's topic for the talk of Dr. Madriti is the process safety and loss prevention via inherently safer design, which is about the approach to some you can say the proactive approach to prevent the accident in the chemical process industry rather than the merely manage them after that the incidents. I have some go through so profile of Dr. Madrati. She is very impressive in process safety and had the PhD from the University Technology Petronas. And luckily, I also have the PhD from the same university. So it is pleasure for me to welcome you, Doctor, in this webinar. So I warmly welcome you and all the other participants in this event, and hopeful we will learn something from you. So it's up to you, Prof, to start this event and to your talk, and we will be the audience for you. Thank you, madam. Over to you, Dr. Madrati.
Thanks, Dr. Saab. I would like to request Dr. Hafiz Shehzad Munir Saab to recite some verses from Holy Quran. So then the Dr. Madhati can give her speech. Doctor, can you hold for a while? So first we can start with the verses of Holy Quran.
Okay, doctor.
So Dr. Hafiz Shehzad Munir Saab.
أعوذ بالله من الشيطان الرجيم بسم الله الرحمن الرحيم إذا جاء نصر الله والفتح ورأيت الناس يدخلون في دين الله أفواجا فسبح بحمد ربك واستغفر إنه كان توابا صدق الله العظيم. Over to you, Doctor.
Thanks, Dr. Hafsa. And now, Dr. Mutati, you can start your speech, and everyone can first listen to Doctor's speech, and then you can, if you have any questions, then you can ask the questions at the end of the session. And I hope Dr. Mutati would be happy to answer your queries. Over to Dr. Mutati. Over to you, Doctor.
Okay. Bismillahirrahmanirrahim. Assalamualaikum and good morning. I believe it's still morning over there, right? So I hope my slide is visible to all of you. Is it okay, Doctor?
Yeah, the slides are visible. So
okay.
I hope everyone can see.
Okay, first of all, I would like to thank everyone for the warm welcome, for the introduction. It's actually my pleasure to be here to talk about process safety. And for today, I'm going to talk about process safety and loss prevention using inherently safer design. I'm going to start my sharing session about how why we need process safety in chemical process industry, as I believe that everyone know that in chemical process industry we are dealing with highly hazardous material, and also we have really complex system. So that's mean the simple mistake making by us can lead to very big accident, very severe accident. So here, for example, I have a few accidents happen in the past. So for example, here I have a Piper Alpha fire and explosion accidents. And the second one is actually the explosion in Pengerang Integrated Complex. This is actually the recent accident happened in my country, in Malaysia. And actually, this is the explosion happened in hydrodiesel treater unit. So we have like some sort of the process, which is we remove the sulfur from raw diesel using the hydrogen. And fortunately, this accident actually happened at night. So most of the worker already going back, clock out from the work. So the impact of accident will be lesser. Then the final accident that I have here, example, this is also the recent one, the Beirut explosion, which is happened in Lebanon. So in Beirut explosion, basically what happened, they have ammonium nitrate, which very explosive, very reactive material that has been used for fertilizer production. Then they store this material without proper safety measure. Then the accident actually happened because the worker actually start the welding process at the door, and the spark actually initiate the explosion. So we already seen that when we make the mistake, the accident happen, then you must remember that the effect of accident not only affect us, not only affect our co-worker, it will be larger, it will be bigger. In fact, it will affect the people outside of the plant, the surrounding community. In fact, it will cause the environmental damage and property damage. So yes, then that's the reason why process safety is very important. That's mean if like you don't manage your process properly, then the accident happen, it will cause billion of losses. Then for that, what we have in process safety is we have process safety management. Basically, process safety management is the collective effort where we manage the process hazard using the different technique or different criteria. So the first is like become some sort of layer of protection to our plant. So the first layer, the basic one, is like we implement inherently safer design strategies. So in inherently safer design strategies, what we do actually, we try first to eliminate the hazard from our system. If we cannot eliminate the hazard, then we try to reduce the hazard, or we try to reduce the likelihood of the hazard. That's the first one, eliminate the hazard. That's what we call the first order inherent safety. Then the act to reduce the hazard or likelihood of the accidents, that's what we call the second order inherent safety. Then after we try to have the safest alternative, the best alternative that we have, then we can add more layer of protection, which is we are going to use the passive system, active system, and procedural to increase the safety level of our plant. In like a passive system, actually what we do, we try to reduce the hazard by like changing the design of the equipment itself. For example, you provide the dike, the dike around your equipment. Then like in active system, what you do, you install the controller safety measure. You also can install the relief valve. That's kind of the active safeguard. Then in procedures, what you have, you can have the standard operating procedure. You also can have the policy. You also can provide the training to your staff. So that's any like the action coming from management for the safety reason. So for today, what I'm going to talk about, I'm focusing on the first layer of process safety management here, which is about inherent safety. So when we talk about inherent itself, it means something existing, something permanent, and something inseparable from our system. And we can say that inherent safety, that means the safety features that embedded in our system, it can be separable from our system. So the definition, actually, we are trying to reduce, or we are trying to eliminate the hazard associated with our process by changing the process itself. We are not rather than we are using the controller or safety add-on. And actually, inherent safety principles actually is like quite the old, I would say, the old theory, because it was first proposed by Professor Trevor Class, the gentleman here, back in 1974. So that's almost 50 years ago. And the reason why Professor Trevor Class actually start with this principle, this is after the Flitsburg accident. So what happened in the Flitsburg accident, this plant actually, they process cyclohexanone where they have this flammable material, a high volume of this flammable material in their plant. And they have like 6 reactor in sequence, like to process their reactant. So what happened actually, yeah, this is reactor number 4 and reactor number 5. Then one day that this reactor number 5 actually out of the service, so they take out the reactor number 5, they connect the reactor number 4 to number 6 with the simple bypassing pipeline. So then they continue the process, and after that, I think they can operate for a few days before the leaking and explosion happened. And after this accident, like Professor Trevor Klatz giving a talk, and he emphasized so much on how this kind of accident can be prevented, can be avoided if this plant having low inventory of hazardous material. The speech, he said that what you don't have, it can leak. That's mean if you don't have the hazardous material, so it can leak in, and it also cannot escalate to the severe accident happen here. So in inherent safety principle, there are 4 main principles that can be used to implement this concept. So first of all, we have minimize, substitute, moderate, and simplify. So this is the 4 principle. So like in minimize principle, what you are trying to do, we can try to reduce the inventory of hazardous material, or we can try to reduce the energy in our plant to make our plant safer. Substitute means like you are trying to replace the hazardous process with the less hazardous one, either process or your material. Moderate principle means like if you cannot remove the hazardous material from your process, you can try to reduce, to make it safer by changing the operating condition. You can try to reduce the pressure, you can try to reduce the temperature of your process. Then the final principles, that mean you are trying to simplify your process. You eliminate the unnecessary complexity, so that means you actually trying to remove the potential of human error, because human error actually one of the major factor that contribute to the accident in chemical process industry. So here, what I have here actually the same concept, but the extension more about inherent safety. But I want to highlight to all of you here, inherent safety actually, you can use this principle at during design stage, but and design stage you have several parts, and you can use the principle according to the stage which is suitable for your stage at that time. So, and okay, and you can see here, this is all the stage for design stage, R&D. You start with R&D stage until detailed engineering design stage. So the earliest you implement inherent safety is the better, because at the early stage, the potential of risk reduction is high and the cost to change the process is low. When you move towards the end, actually the cost will increase and the potential to reduce the risk will be lower. And after that, actually, after you complete the design part, you are having like the construction part, the testing part, and also the operation part. At this time, it's actually too late for you to implement inherent safety principle, but you can use the active, passive, and procedural to reduce the hazard. So here, other than safety reasons, what is the reason that you need to use inherent safety? This is because of the cost, the economic reason. If you can see here, perhaps when you want to implement inherent safety, you see that you are having like high operating costs, but in reality, throughout the times when you are having the life cycle of your process, you are actually reduce the cost of your operating, because if you see here, okay, inherent safety actually the first layer of your safety protection. That means if you can eliminate or reduce the hazard at this stage, you can reduce the passive and active strategies over there. That means you reduce the requirement for your controller and safety measure. when you reduce the number of your controller, that means you are reducing the cost for maintenance, for testing, for training the expert staff to handle your hazardous process. So now we already know what is inherent safety, the basic principle. What I want to share with all of you next is the example of inherent safety application in industry. So we go one by one. This is the classic example of a substitute principle where you are trying to select the safest reaction chemistry. So obviously this is the earliest stage when you start to design your process. Okay, I have the example of very hazardous, very toxic material, which is methyl isocyanate, MIC. This is the material that responsible for the death of 1,000 people in Bhopal accident back in 1984. So, but until now, people still using this material for fertilizer production. So here, the process route I adapt here is actually coming from Bayer Crop Science report. What happened in this plant, actually, they have the methyl isocyanate in their plant, and actually the explosion happened and the near miss accident almost caused the MIC to release to the surrounding environment. So because of that, the investigation body asked them to conduct the inherent safety assessment, because they found from the investigation that Bayer Crop Science, they didn't implement inherent safety, but they relied on the active and passive strategies to reduce the hazard. So this is the process route. So the first one, actually, the process route they use in this plant. So this is coming from UCC process, the patented process. So they produce methyl isocyanate using methyl carbamyl chloride. So in this process, they have like low pressure and high operating temperature, and they are operating in like the batch process. And you know, like the batch process, the concept of batch process, that you have to hold like the large amount of the material in your plant. So to reduce the amount of MIC, they propose the second process route where they produce methyl isocyanate using methyl formide. So this is the DuPont process. So DuPont process, in this case, they are operating at high pressure, high temperature, and they produce methyl isocyanate in the gas phase. Because of the gas phase, the MIC actually need to be supplied to the plant for one-time use. So that means they eliminate the high inventory of methyl isocyanate. So because you just supply and it was consumed immediately in the process. And the third alternative is like the cyanate process patented here. So in this alternative, actually methyl isocyanate has been produced using sodium isocyanate. And in this alternative, actually the methyl isocyanate was produced in like, again, in the batch process, but the inventory will be lower than the first option. So here, clearly the second alternative is the safest alternative for substitution principle. So the second substitution principle that example that I can show everyone is like the replacement of the solvent, either like in the concrete sealer here or in the paint. So we have like the normal paint, which is we have solvent paint, and we also have the water-based paint. The solvent paint, actually they have like volatile organic compound which is hazardous to our health, and also some of them have flammable properties. So to eliminate this hazard, we actually trying to replace the solvent with the water-based system. Sorry?
Anyone want to ask the question?
Yes.
Otherwise, if you don't have any question, please switch off your mics so doctor can deliver her speech.
Is it okay? If okay, I will continue my sharing.
Doctor, please continue.
Okay. So this is the substitute example. And we move to minimize example. This is for methyl acetate production process. In this process, actually, we try to minimize the amount of hazardous material, actually using the reactive distillation column. So in reactive distillation column, actually, they combine the reaction part and distillation part in one equipment. So here, rather than they have like one reactor here and 8 distillation here, they can simplify the process to one reactive distillation column and another to the normal distillation column. So basically, in this case, it's not only minimize the inventory, it's not only minimize the amount of auxiliary equipment, is also actually we have the simplification process here. With the simple process, you can operate your process easily and you can avoid the mistake. And yeah, the next example of minimization, actually the type of reactor. I believe that everyone know about this. This is the basic reactor that maybe we have covered in like chemical reaction engineering subject. So in case that you have this kind of reaction, the reactant A and B, and you have the catalyst C, and you produce like product D and E, and actually this is the exothermic reaction, then it release the heat over here. So if you have this process in the batch process, that means you have to have a large inventory of hazardous material. And if like you have over discharge of reactant B to your system, so you have the potential of explosion here in case like this is a reactive or explosive material. So to avoid this kind of hazard, what we can do, we can change to the continuous process. So in continuous process, it depends on the type of your reactor, it depends on the type of your process. You can choose the type of your reactor. Either you want to use CSTR, packed bed reactor, or PFR reactor. So here, by changing this part, you are having the smaller inventory of hazardous material. So that's mean like the reactant feed to the system at the same time. After the completion, they discharge continuously from the system. And the next example is the example of moderation. So here, let's say in the process that you have hazardous material, in this case ammonia. Ammonia is like really toxic material, but we cannot eliminate the use of ammonia, for example, for fertilizer production. So what you can do, actually, you can try to change the process condition to make it safer. Here, what you can do, you can dilute the ammonia. Instead of you're keeping the high purity 100% ammonia, you can like move to aqueous ammonia. And you can see here, when you like goes to aqueous ammonia, actually when the release happen, so the concentration of ammonia release for aqueous ammonia would be lower, so that means safer from the anhydrous ammonia. And another one actually, because ammonia in like ambient temperature, they exist in the gas phase. So usually we start using the in the liquid phase because of economic reason and also for the safety reason. So we also can try to reduce the liquefy the ammonia. So like in the case of release, in the case of ammonia release to the surrounding, it's like form the pool around your equipment before it start to evaporate and traveling, instead of when you have like the gas ammonia, it straight goes to disperse to the surrounding. And I think another example, which is this time around we are implement the simplification process. So in this example, actually what we have here is like the low temperature process where you have the flow of the material at negative 40 degrees C. So the problem here, the compressor here unable to cater the temperature of reactant lower than negative 50. So that's mean in order for them to maintain that one at negative 40 degrees C, they have to install the controller here. First the controller here, then the second one they have to install here the temperature trip. So that's mean if like the temperature controller here fail, then the temperature trip here will take action, will shut down the compressor. So this is the conventional design, but if you implement inherent safety strategies, what you can do, you can try to change the material of this compressor. You will you need to use better grade of steel for the compressor, so that if like it can cater the flow below negative 50 degrees C, you can remove this instrumentation. And okay, this is another example for simplification. So simplification in this case, we have several boilers and we also have the steam supply system over here. But here you can see that we have like quite a confusing labeling for our valve. So you have D1, D2, but D2 and C1 is like parallel with each other, and D3 and C2 parallel with each other. So to avoid confusion, either you can try to make the label clearly, or another one is better if you can have a different steam supply system for the reboiler. Perhaps this can avoid the confusion and mistake while operating this equipment. So now we already like know the principle of inherent safety, why we need to implement inherent safety, the example. Then what is the current status of inherent safety implementation right now? So here I have like the survey coming from the literature. Actually, it has been done quite for some times. The reasons why people are not using, not implement inherent safety in their design. The first reason, they said that we are safe enough or no regulatory requirement, which is 80% from the respondent, which is, I would say that throughout the years, our regulation become better, and if we go through the safety regulation, it's actually stated that you first need to implement inherent safety. But what is lacking in this part actually for me is the enforcement of the regulation itself, because the lack of enforcement, people like they jump straight to the active and passive measure to control the hazard. They not even consider inherent safety for their design. The second reason, they said that the lack of suitable inherent safety method. In this case, there's much more progress and improvement done in this area. I would say like starting from 1999 until now, people keep developing the methodology to assess the safest alternative or inherent safety design. So they start with like index-based methodology, because they said that at the early stage of process design, there's a lack of data, so you need the simple indicator to measure your safety property. So that's why they come up with index-based methodology. And later on, they feel like index-based methodology is not enough. They want something that more reliable, so that people move to consequence-based methodology and risk-based methodology. Definitely, this is the better method to measure the safety of our process, but it will take longer. It will take sometimes for us to perform the evaluation compared to the index-based methodology. For the second problem, we already solved this kind of problem, and I believe that many more works will come later. And the interesting part is like the third reason, which is taken 64% of the reason here, which is the industrial practitioner, they feel that unconvinced of the benefit of inherent safety implementation, including the cost, although we already said that by implement inherent safety, you can reduce the cost for maintenance, you can reduce the cost for training, you can actually lift up the image, the company image. Then they are still not convinced. Then I think that's a particular problem coming from this part, the second part here, which is what we call inherent safety conflict. When we want to, the principle of inherent safety, it seems like very simple, but the implementation is not straightforward. When you want to consider inherent safety, so that means you need to consider the whole process. You need to consider, you need to understand your process, you need to understand the trade-off when you implement the inherent safety. So here we have like the conflict between inherent safety principle itself, we have the conflict between inherent safety with environment, we have the conflicts of inherent safety with economy. And one more issue is like are you really implement inherent safety to reduce the hazard, or you just transfer the hazard from one place to the other place? What I said by this, that's mean, for example, you said that you minimize the amount of hazardous material in the plant, then you said that you implement inherent safety. But at the same time, in order for you to fulfill the requirement of your process, that's mean you need to have the frequent transportation to supply the material to your plant. So that means you are moving the risk from your plant to the transportation part. So this is the thing that you need to consider. And to give you a better like understanding on what I'm talking about inherent safety conflicts, we are going to go to see again the conflict actually happen in the example that I have shown here. So in the first process, when we said that the second process is the best process, the safest process, At the same time, this process actually they produce a high impurity of the final product. So that's mean if like the plant owner want to change the process from this to the second process route, that's mean they need to install more distillation column in their system. So that's the conflict you see between inherent safety principle. You substitute to make your process safer, but at the same time you are having the more complex system. You have additional equipment in your system. And like the third one, actually, when if you implement this process, they actually produce much more waste compared to the first process. And if like in plant, you know, like when you have the schedule waste, then that's been additional cost for you to treat the waste. So that's the conflicts happen in the first example. In the second example, yeah, this is the solvent replacement for paint and coating industry. I want to share with all of you what I have encountered when I'm working with this industry. So the reasons why we cannot convince people to select water-based paint, which is we call it the safest alternative. What happened? We have a major car manufacturing company that looking for the third party company to they actually in the car manufacturing company, they only like produce the body the car body part, and also they assemble the part, but they outsource the painting process to the third party company. They open the tender, and definitely the one that submit the proposal with the lowest cost will get this project. So the third party company, actually the spraying a house, actually contact us as a paint supplier. So they said that they want the paint for car body part. So we give them 3 proposals. So the first proposal is like the solvent based paint, which is clearly highly hazardous, but we have the lowest cost over here. Then the second alternative, what we give them is like what we call eco paint. In eco paint, actually, we are still using volatile organic compound as our solvent, but we remove these 3 kind of solvent, which is toluene, benzene, and xylene, because the previous research showed that this kind of solvent can lead to the cancer. So this is definitely safer alternative than the solvent, the complete solvent-based paint. So that's the second alternative. The price will be in the middle. So, and the third alternative, we have actually the water-based paint. We also give the this proposal to them. Then water-based paint actually the price at the highest side. Then other than that, compare with the solvent-based and eco-based paint, they actually have a slower drying time. So that means if they use this water-based paint, it will increase their production time. So that's the issue. The first one is the price, and the second one is the performance of the paint itself. Then coming the third part, where water-based paint actually is more sensitive to the surroundings. So that means when you spray the paint, the dust really easily attached to the surface. So you will have like the reject part of your spraying process. So and if you want to solve this kind of problem, that means the spraying house, they need to have the separate line between the project that having the solvent-based paint and water-based paint, which is the company cannot do that, because other than this project, they have another project that they are dealing with time. So for that reasons, the company actually first trying to settle with the cheapest option, which is solvent-based paint. Then, fortunately, there's a regulation saying that for interior part of the car, the paint must at least we need to use the eco-based paint. So they don't have any choice. They have to get the eco-based paint, which is a little bit higher price, but the safer alternative. But they definitely cannot use the water-based paint. So yeah, that's kind of a conflict that I would say that will hinder the implementation of inherently safer design and in real life practice. Then in here, like the conflict within, like here, the example of reactive distillation column. We said that we simplify the process by like reducing the number of equipment here, but to control the combined equipment, reactor and distillation column, you definitely need to have more complex control system, which is the complexity versus complexity of the overall process with the complexity of single equipment. And this is also the conflict with simplification process. Here you need to handle the valve well, because you need to make sure like reactant B will fit to the process slowly as like needed for the process. So again, minimize versus simplification. And here, like again, in dilution process, safer when you dilute the process, but how about your final product? Are you going to have the same purity? If not, then are you going to install more distillation column to achieve the same spec? That's kind of the kind of consideration that you need to consider. Simplify. Okay, here you have the changing of material construction to make it your process safer, but here is like inherent safety versus cost, because when you have like high reliable higher steel grade, so that's mean the price will be higher, than you need to calculate all the things again. This is also the simplification versus simplification process. If I said that we can simplify, avoid the mistake doing by people by providing separate steam supply, but at the same time we actually adding more equipment. So simplify the labeling, but we actually adding complexity to our process. So now we know the reasons why, although this is very good principle, it has the potential to offer you the safer process, and it can reduce the cost for your process if the concept has been implemented properly. We already know the reasons why people like really not really keen to implement this inherent safety principle. The basic reason, because you need to have deep understanding about your process, which is perhaps, yeah, you need the experts in your plant that know the process very well, so that they can advise you on that. But yeah, so we know the reasons and we know the problem, but looking at the current trend where we are moving towards the IR 4.0 and big data, I think that is like very useful if we can use the big data concept to solve inherent safety conflict, so that we perhaps can reduce the time, we can reduce the dependency on the expert judgment. I think with that, I need to recap again what I have discussed here. It's like why we need process safety, then the concept of inherent safety principles. Why we need inherent safety is not because of safety reason only, it's also because of the cost part, the economic part. Then I also like share with all of you the few examples, and I also share the conflict that might hinder the implementation of inherent safety in the real life practice. And yeah, as a conclusion, I think we still have a chance to improve the part if we can implement big data for inherent process safety. With that, I think we come to the end of my sharing session. Hopefully my simple sharing here will encourage people to think more, to make safety as their culture, as their way of thinking when they're designing the process. With that, I think thank you for your time and attention.
Thank you very much, Doctor, for your presentation. Now I would like to open the floor to audience. To if they have any question, they can ask Dr. Mazati, and she will be very happy to answer your queries. Especially the students who are studying the process design in this semester. I think so they might have some interest in this concept of process design, because enhanced safety is a bit related to process design, while the other process safety strategies are not related to design. They are trying to address or suppress the issues. However, this is trying to make the process safer from the very start. So if anyone has the question, please ask the question freely. Also, the students from master or PhD, they can also ask the questions if they have any questions, or any person who is interested in process safety. So the floor is also open for the faculty members. If they want to ask any question, there are number of faculty members also available in this session. So if they have any question, or if they have any interest in process safety, so they can ask Dr. Mathadi. I guess no one has the question. So I'm very thankful to Dr. Madhati for your time and your efforts to spare your time for our students as well as for faculty members to guide them or to share your knowledge about process safety and specifically for the inherent safety scheme. And we thank you very much again. I thank you on behalf of my chairperson, Dr. Muhammad Saveer, as well as all the faculty members and students of Chemical Engineering Department for the Free University. So we are, thank you very much, and hereby the session is closed. Thank you very much, everyone.
Thank you, Doctor.
Thank you, sir.